Have you noticed while counting, when you start counting from 0, 1, 2, 3, 4 to 9, you then count up by writing down the same numbers again and again. So what I am saying is you write 0 to 9, then you again write 0 to 9, then you again write 0 to 9. If you don't believe me, see this. This is counting from 0 to 9. Then again you count from 0 to 9, just appending the numbers in ascending order. We build numbers in ascending order. So this is a fundamental rule that applies to all number systems. Let us take example of other number systems. In octal number systems, we count from 0 to 7. We run out of these 8 numbers. No other drawing or symbol is possible in base 8 system. We again write down the same series, again write down the same series as the fundamental rule we have been using. Append the numbers to make them look different from these numbers and thus keep counting on in ascending order. If we compare these two number systems, 7 and 7 both are same, so this magnitude is same with this magnitude. But when we have 8, its equivalent representation in base 8 system or octal is 1010. In contrast, hexadecimal number systems have actually 16 different drawings, which again by our fundamental rule is repeated, and just by appending a number before these 16 different drawings, we can create different number sets, and we can keep going on by using all these different numbers in the higher magnitude place, and when we run out of all these, we will again increase one more place and then do the same or apply the same fundamental rule. So let us apply the fundamental rule to binary number system. Binary number system has got only two drawings, 0 and a 1. Let us start writing the numbers in binary number system, say with two places. So 0 is represented like this. We count up, 1 is represented like this. Notice we have run out of our numbers or drawings for base 2 binary system. What we do is we obviously use the fundamental rule, write down the same thing again, but since we have already used this in higher place, we will now use this in higher place, and we have successfully counted up in binary number system also. So this is 0, this is 1, this 10 represents 2 in decimal, this 11 represents 3 in decimal. If we had 3 places, what would we do? We would keep counting like this. So we have run out of numbers here. We will write this new number here, and we can copy all the numbers on the lower places and append with the number to keep counting up. So increasing the places allows us to create different drawing from the previous drawings, and thus we can keep counting to infinite numbers by increasing the places, just having certain amount of drawings. So 2 drawings available in binary system, 15 in hexadecimal system, 8 in octal system, and there are 10 different drawings in decimal number system. The number 21 can be written as 20 plus 1. So this can be further written as 10 times 2, which is 20, and 1 times 1, which is 1. Further, it can be written as in powers of 10. We can write the same equation. 10 to power 1 is 10, times 2 it will be 20 again, plus 10 to power 0 will be 1, into 1 will be again 1. So what we are doing is we are representing the decimal number with base 10. We are representing this decimal number which has got base 10 in expanded form, expanding it to a point where we can pull out tens, which is the base of this system. So we can now see that the places can be arranged in increasing orders to have weights. This is units place, 10 to power 0. This is tens place, 10 to power 1. This is hundreds place and thousands place, 10,000s, and so on. So the numbers can be generated using weights also. Suppose we have to write 921. So we need 9 hundreds, 2 tens, and 1 ones. So that is 921. So this is how numbers are generated from weights. Here I have compared the weights of different number systems. Base 10 has these, base 2 has these weights, 2 to power 0, base to power 0, base to power 1, base to power 2, base to power 3 happens in all the number systems. So these are the weights for the number systems. I have taken an example. Let us represent 9 in decimal number system. So we'll pick 9 ones to give you 9. In binary number systems, since the set has only 2 different drawings as compared to base 10, so how do we get 9 here? We pick out 8 ones, that will give us 8, and we'll pick out 1 once. So 8 plus 1 will be 9. So in binary we write 9 like this. In octal we will pick out 8 ones and 1 ones will give you a 9. So 9 is represented as 1 1 in octal. We'll write the number like this. Okay, so we'll write this number like this and so on. So you can one thing to note, 9 is same in hexadecimal as it is in decimal. Another example, let us represent 20. 20 will be represented by these bits in binary, like this in octal and like this in hexadecimal. Let us work out one of these. Why it is 1 4 14? Because we need 16 weight 1 times, so it gives 16, plus we need 1 weight 4 times. 16 plus 4 will give you a 20. So this is hexadecimal representation of the decimal number 20. There is another way to convert or represent number systems. Suppose we have the number 4 and this is in base 10. How do we write it in binary? We repeatedly divide the number with the base. So the base is 2, the number is 4, needs to be represented in binary. We divide this number by this number, so the factor is 2, which divides this exactly, gives remainder 0. So 2 then again divides this number with factor 1, gives remainder 0. 2 tries to divide but remainder remains 1. So we arrange this number in this fashion and get the binary equivalent. So this is another way of representing numbers. In case of decimal points, suppose this is base 10, you want to go for binary representation, you repeatedly multiply the decimal part with 2, get the numbers. These numbers will represent your MSBs, and keep multiplying the decimals when we reach these kind of numbers, just pick the decimal and keep multiplying them with the base to get different numbers. So these may end, they may not end. If they do not end, just pick the numbers from here, arrange them in this fashion to get the decimal equivalent of binary number. We can apply this technique on decimal number itself. Base will be 10, divide the number that is needed to represent it in decimal. So it tries but cannot divide, so remainder is 4, and that is the MSB, and that is the number. Another example, let us try to convert 48 into base 10. It is already in base 10, but let us apply the rule. So applying the rule, dividing by the base 10 gives you 10 fours are 40, remainder is 8. 10 zeros are 0, remainder is 4. Arrange them according to the rule, you get the number again. Okay, so it applies to all number systems. Methods to convert or represent numbers. First method was using counting fundamental rule by arranging the set of numbers of a system in such a way that we can build new drawings, new numbers, and keep counting up. Second way was to use weights of the number system. Third way was to use the division method. Now fourth way is to use the calculator. Simply you write any number. So I have written the number, let us say 11. In decimal it is represented like this. In binary it is represented like this. In octal like this. In hexadecimal like this. So our calculator is also a handy tool. It's a computer to compute it directly for us. So 4 methods to represent, convert numbers.